I am Professor A.K. Patnaik. I have already taught few chapters on physical chemistry, and today I will teach the wave mechanics. The first topic of wave mechanics is de Broglie equation, that is your matter waves. So, Newton suggested the dual nature of light. The light behaves as a particle as well as a wave. So, this idea led the de Broglie to suggest the matter waves. De Broglie suggested each material particles, electron, proton, neutron, atoms, when they are in motion, they are associated with the wave. That wave is called matter waves. So, this proposal put the foundation of the wave mechanic theory of matter. So, that is the wave mechanical theory of matter. So, if a particle behaves as a wave, then it must have wavelength. It must be characterized by wavelength. That wavelength is calculated by de Broglie equation. If photon like light, electron also behaves like a wave. If you consider a light particle, its energy is given by E is equal to h into nu, and Einstein's mass energy relation E is equal to mc square. So, these are the energy of the electron. So, h mu is equal to mc square, or we can write in place of mu we can write c by lambda, where c is the velocity of light, that is equal to mc square. C cancel. So, lambda will be equal to h by mc, mass into velocity of light, which is equal to h by momentum. So, this is the wavelength associated with the particle of light, that is your photon. So, when photon behaves as a wave, its wavelength is expressed as h by mc, mass of the photon, into velocity of the light is equal to h n by p momentum. Similarly, a material particle like electron, like proton, neutron, atom, when is in motion, it also associated with the wave. So, that wavelength is, if m is the mass of the particle and v is this velocity, then its wavelength associated with is expressed as h is equal to m into v, or is equal to or h by p. So, this wavelength is associated with the material particle. This wavelength is associated with the material particle. So, if a particle is in motion, then it is associated with the wave, that is wavelength is expressed as a ratio of the Planck constant to the momentum. For example, let us see a tennis ball. Suppose a tennis ball is 100 gram, mass is 100 gram, and it is moving with a velocity 100 centimeter per second. So, this is your equation is called de Broglie equation. That is, we can by using de Broglie we can calculate the wavelength associated with a material particle. So, if a tennis ball of 100 gram and if you throw it, it will move with a speed of 100 centimeter per second, then what is the wavelength associated with? We can calculate by using this formula. So, let us see what is the value. So, this is equal to h is equal to 6.62, since it is centimeter, we will use 10 to the minus 27 R per mole. Now, so the mass is equal to 100 gram and velocity is equal to 100 centimeter per second. So, wavelength associated will be equal to 6.62 into 10 to the power minus 31 centimeter. So, if a tennis ball of mass 100 gram is thrown with a velocity of 100 centimeter, it is associated with a wave. Its wavelength is 6.62 10 to the minus 31 centimeter. Now, this wavelength you can see what is its power, 10 to the 31. So, this wavelength is very small. So, it is very difficult to detect or to measure. So, a material particle is associated with a wave, macroscopic particle associated with a wave, but that wave is very small to be detected. Now, if you consider an electron, let us see an electron, and a mass is known. What is the mass of the electron is 9.1 10 to the 28 gram, or if you take kg it will be 31, and suppose it is moving with a velocity 10 to the 10 centimeter per second, 10 to the 10 centimeter per second. Then using the de Broglie equation, we can calculate what is the wavelength associated with the electron, that is 6.62 into 10 to the minus 28 by 9.1 into 10 to the power minus 28 gram. In CGS system everything 10 to the power 10. So, this is equal to 10 to the power 10 to the power 10 velocity. So, this is equal to, we can calculate that this is equal to 7.72 into 10 to the power minus 10 centimeter. This is the wavelength associated with the electron moving with a velocity 10 to the 10 centimeter per second, or we can write this is equal to 0.072 angstrom. So, when a electron is moving with a velocity this 10 to the 10 centimeter per second, its wavelength is very small, 10 to the 10. So, you can see the comparative with 10 to the 31. So, it is in angstrom, it is 0.072 which can be measured and can be detected. So, for a microscopic particles macroscopic particles, we can calculate the wavelength, but we can measure the wavelength for microscopic particle like electron. Now, the question is, this particle is called material particle. Now, what is the experimental proof for this electron associated with the wave? That is called experimental proof of wave nature of electron. Experimental proof of wave nature of electrons. The two scientists, one is called Davis and Germano experiment. In 1926, Davis and Germano suggested the wave nature of electron. So, what they did? They have taken a nickel crystal. This is a nickel crystal. Now, they allow to fall the beam of electron. This is your beam of electron. Allowed to fall on the nickel crystal. So, the reflected beams are allowed to pass through the photography plate. So, the reflected beam are allowed to pass through the photography plate. So, in the photography plate, when development, so the large number of concentric rings like this you develop, will see such type of diffraction grating, that is called diffraction grating for nickel crystal. Now, same type of grating we get if you pass, instead of electron beam, you pass the X-ray. Since X-ray is a wave and beam of electron also behaves as wave, because the diffraction patterns are same. And from this calculated the wavelength is calculated. From the experimental value we can calculate the wavelength, and wavelength is also calculated by using de Broglie equation, both are nearly same. So, they proved that the beam of electron behaves like a wave. The another experiment was carried out in 2007 by Thomson. Second is Thomson experiment. In 1927, Thomson proved that beam of electron behaves as a wave. How? Now, this is the source, this is the slit, this is the gold foil, this is the photography plate. So, you will see this type of rays, reflected rays will form like this. And this ray will form a spot. So, Thomson carried out when this is the source of electron, it passes through a slit and passes through the gold foil experiment. It is Thomson carried out the gold foil experiment, where they allowed to pass the beam of electron through the gold foil and allowed to fall on the photography plate. On development, it also show around a black spot there are several concentric rings. The similar pattern is also observed by X-ray. Since X-ray is a wave, so beam of electron also behaves as wave. So these two experiments confirm that beam of electron behaves as a wave. So it is concluded that not only beam of electron, the beam of neutron, beam of proton, beam of atoms, so any material particle behaves as a wave. So what is that wave? That wave is called matter wave. So what is the difference between electromagnetic wave and the matter wave? Electromagnetic wave or radiation and the matter wave. Now, number one, electromagnetic radiation or electromagnetic wave. In electromagnetic radiation, there is electric field and a magnetic field perpendicular to each other. So, electric field and magnetic field are perpendicular to each other. Electric field and magnetic field are perpendicular to each other. In case of electromagnetic radiation or electromagnetic wave, there is no such field. In case of matter waves, there is no such field in case of matter waves. Second, the particles in electromagnetic radiation travel with the velocity of light. This particle, as we have shown calculation that the tennis ball will also have a wavelength. So, this velocity of light, different velocity depending on the particle. Third point, for the movement of matter waves, no medium is required. But it requires a medium. The fourth difference is that the electromagnetic radiation is emitted from a source. It is emitted from a source. But here it is not emitted, it is associated with the moving particle. So, the matter wave discovered by de Broglie is different from the electromagnetic wave by these 4 points. Then comes Heisenberg. The second part is the Heisenberg's uncertainty principle. What is Heisenberg's uncertainty principle? After the suggestion of the de Broglie that electron not only a particle, it also behaves as a wave. So, when it behaves as a wave, when we are going to locate the position of the electron or we are going to measure the position of the electron, and since it is a wave, we cannot get the exact value of the momentum at the same time. So, this creates a problem, how to get the velocity of the electron as well as the position of the electron at the same time. We cannot get it because of the problem that it behaves as a wave, it is not only a particle. Therefore, this problem was solved by Heisenberg's uncertainty principle. The Heisenberg's uncertainty tells that it is impossible to measure simultaneously the position as well as the momentum of a particle, let us say electron, with absolute accuracy. That means if we determine both the position as well as the momentum at the same of a electron at the same time, then it is not absolutely correct, because there is a error in determining the position as well as the determining the momentum if you do both the things at the same time. If delta x, so it can be mathematically presented, if delta x is the error in determining the position and delta p is the error in determining its momentum, then into this into is equal to some constant, and more accurately this is equal to h by 4 pi. So, this is the mathematical expression suggested by the de Broglie, suggested by Heisenberg uncertainty principle. Now, if delta x is the error and in determining the position, delta px is the error in determining the momentum along x axis. If delta x is very small, that means error is minimum, then there is uncertain, then delta x will be equal to 1 by delta p. If this error is very small, then delta px will be uncertain, because this will be, this error very small, this is large. That means if this is certain and this is the uncertain. So, the product of two error is a constant quantity. We can also verify this from the experiment. Now, let us take an arrangement of the experiment by which we can prove that delta x and delta px is a constant quantity. Now, let us, it can be possible, we can measure, for measuring the position of the electron we require the microscope, and to see the electron position we require the light arrangement. So, by means of a light and high power electronic microscope, and we can experimentally prove the Heisenberg's uncertainty principle. Let us see, this is the position of the electron, let it equal to O. Now, this is the beam of light, that is your beam of radiation. Now, this is the position of the momentum. So, this is the position of the microscope. So, this, suppose this is your lens. So, this is your source of light. Now, this is the micro lens, the one can see here. Here you can see the observe the position of the electron, and this is the light illuminated to locate this position, and we can see through this microscope. Now, O is the position of the electron. So, we can see the position of the electron through this microscope. Now, if you look determine the exact position of the electron, there is some error in the instrumental instrument, that is a microscope, that is called resolving power of the microscope. So, the resolving power of microscope is delta x is equal to lambda by 2 sin theta. That is the resolving power of the microscope. That means this is the minimum error while you determine the position through the microscope. That is the resolving power of the microscope. So, delta s is equal to lambda by 2 sin theta. So, our aim is to find out what is the value of delta x and what is the value of delta px, then you multiply, find out what is the product. Now, to determine the delta px value, let the lambda is the lambda dash is the wavelength of incident photon. Let lambda dash is the wavelength of incident photon, and the momentum h by lambda dash is the momentum of incident photon. Let lambda is the wavelength of scatter, this is the scatter radiation which makes angle theta with the axis of the microscope. This makes theta with the axis of the microscope. So, lambda is the wavelength of scatter radiation. So, wavelength of, so lambda by p is the momentum of scatter radiation. That means if this is a momentum is equal to h by lambda dash, and the momentum here, the scatter radiation is equal to lambda h by lambda dash, the momentum here will be equal to h by lambda. This is h by lambda. So if the momentum of the incident photon is h by lambda dash, scattered photon is h by lambda. So we want the along x-axis. So if you consider this scatter radiation h lambda, then what is momentum along x-axis? So momentum along x-axis of the scatter radiation, momentum along x-axis will be equal to, it will be minus h by lambda sin theta. So for such radiation, what is the momentum imparted to the electron? The momentum imparted to the electron is h by lambda minus h by momentum of the scattered momentum of incident photon minus h by lambda sin theta. Let us say this is your equation 2. So if you consider this scatter radiation and its momentum along x-axis, then what is the momentum imparted to the electron, that is h by lambda minus h by lambda sin theta. Similarly, consider the OB, the radiation along OB. So the momentum along OB is equal to, this is along OA, and along OB will be equal to similarly h by lambda dash, and this will be plus h by lambda sin theta. This is equation 3. So what is the error in determining both the position, the momentum? That is how much of the momentum is transferred to the electron. So the momentum error in determining both the position is equal to, that is your delta px is equal to h by lambda dash plus h by lambda sin theta minus h by lambda dash minus h by lambda sin theta. So this is the error, difference of error, the momentum, measurement of momentum, that is the momentum transfer to the electron due to the collision of the photon with the electron. So along the x-axis. So this value will equal delta px is equal to h by lambda dash plus h by lambda sin theta minus h by lambda dash plus h by lambda sin theta. So this will be cancelled. So the remaining is equal to delta px will be equal to twice 2h by lambda sin theta. So we know the delta px 3 and equation 4. We know the delta x value, we know the delta px value. Now multiply. If you multiply delta x with the delta px will equal lambda by 2 sin theta, and that is equal to, and this is equal to 2h by lambda sin theta. So the sin theta will cancel, 2 cancel, lambda cancel, what is left? So delta x into delta px is equal to h, means it is a constant. So the product of two uncertainty is equal to a constant quantity. That means one is certain, other is uncertain. This is called uncertainty principle. I can give you a simple example. If I will say I have taken my meal and come to the college at 10:30 a.m. So that means we are doing the two things. We are taking our meal at 10:30 and coming to the college at 10:30. This cannot be possible. If one is accurate, other is inaccurate, means either I have taken my meal at 10:30 or I have come to the college at 10:30. Both things cannot be done at the same time. So the message for the Heisenberg principle that the two things cannot be done at the same time. If two things are done, one is correct and other is incorrect, inaccurate. This is the limit of the nature. Therefore, two things cannot be done at the same time. This is the principle, this is the Heisenberg's uncertainty principle. The third part is the Schrodinger's wave equation. So after the discovery of the matter waves or the particle associated with the wave, this idea strikes to the mind of the Schrodinger. There is a French physicist who suggests that the Schrodinger suggests that if a material particle is associated with a wave, then it must have a certain wave equation. What is that equation? That is Schrodinger equation. He derived taking the particle as an electron. So, he derived this wave equation, that is Schrodinger's wave equation. The Schrodinger wave equation is based on two assumptions. Number one is based on two assumptions. Number one is de Broglie equation. It used the de Broglie equation for derivation of the Schrodinger's wave equation. Number second is classical wave equation in a stress string. So, these two equations are used to derive the Schrodinger wave equation for any material particle. That is equal to the de Broglie equation. You use the de Broglie equation and classical wave equation in stress string. That means you put a string and tie in one end and put a distance to the ring, so it will produce a wave. That wave is called wave in a stress string. Or you put a stone to the pond, we will see the circular waves are moving around that spot. These are also known as also known as classical waves. So, these are the similar type of stress string. So, this by taking this equation in a stress string, we can calculate the we can derive the Schrodinger's wave equation. So, if this is the wave equation of the electron, then let y is its amplitude, and its coordinates are x and t. If this is the wave of the electron, then that is similar to that of the wave in a stress string, that is, so its amplitude is y and whose coordinates are x and t. So, we can write the classical wave equation in a stress string as d square y by dt dx square is equal to 1 by v square and d square y by dt square. This is the classical equation in a stress string. From this equation, we will derive the Schrodinger's wave equation. Now, this is the equation 1, stress string, the basic equation, where y is the amplitude. This y's amplitude is a function of, depends on x and t. That means it is a product of two functions. One is a x coordinate, other takes part of the t. So, we can write y is equal to fx into, there are two functions, one take care of the x and other take care of the time t. So, now you differentiate, now look at here, here we require d square y by dx square. So, differentiate with respect to x, then you differentiate to the second differentiation with the x. So, d square y by dx square you can get, and similarly you differentiate with respect to t, then again differentiate with respect to t, we will get this value. So, we put these two value in this equation 1. Now, let us take differentiate this with respect to t. So, if you differentiate this dy by dt, what will happen? This is independent of t. So, we will get fx. So, prior to that, what is the expression for function of t? So, gt is a function of sine function. So, time function is a sine function. We can have a is equal to a sine twice pi mu t. So, a gt is a time function, is a sine function, a sine twice pi mu t, where mu is the frequency of vibration and v is the velocity of progress of the wave. Now, you put this value in this equation. So, y will be equal to fx a sine twice pi mu t. Okay. Now you differentiate this with respect to t. So this dy by dt. So if you differentiate with respect to t, we will get a, this is equal to twice pi a mu, then this is equal to cos twice pi mu t, and this is your fx. Okay. Now again differentiate with respect to t, so that we will get d square y by dt square. Again differentiate with respect to t. So it will be d square y by dt square will be equal to how much? A, this is equal to 4 pi square mu square, then this cos will equal to sine. If you differentiate cos with the sine, this will equal negative and become sine twice pi mu t into fx. Now we put a, what is this gt? Gt is equal to a sine twice pi mu t. So in place of a sine twice pi mu t, you put the gt. So the equation will be equal to, so d square y by dt square will be equal to minus 4 pi mu square, and this is equal to fx function and gt function. Let it, this is equation 2. Okay. Now we will get this value. Now differentiate this equation y is equal to fx a sin t with respect to x. So dy by dx, that means this will vary but this is constant. So it will be a sin twice pi mu t will be equal to dfx by dx. Again differentiate with respect to s. So d square y by dx square is equal to a sin twice pi mu t d square fx by dx square. Okay. Now let it equation 3. Now put the value of equation 2 and equation 3 in equation 1. Put this value from equation 3 and this value from equation 2, this value. So the final equation will be equal to how much? So that is equal to d square by d square will be equal to a sin twice pi mu t d square fx by dx square, which is equal to how much? 1 by v square, that is equal to minus 4 pi mu square fx and gt. Here it is 4 pi mu square fx gt. Here it is what is a sin twice pi mu t d square fx by dx square. We have left one thing, gt is kept constant. So we have forgotten here, gt is also constant here, gt. So here it is also gt. Now gt will be cancelled. So what is left is, and a sin pi, here in place of a sin twice pi mu t, we put gt. So this is equal to, in equation 3, d square fx by dx square into gt. So here is d square fx by dx square is equal to into gt is equal to 4 pi mu square fx gt. So gt cancel and it is minus here and it is left is v square. So put v is equal to lambda into mu. So d square fx by dx square is equal to minus 4 pi mu square fx divided by lambda square mu square. So mu square is cancelled. So what is left is equal to d square fx by dx square is equal to minus 4 pi fx by lambda square. Now this is the Schrodinger equation for one component, one direction along x-axis. Now for 3 coordinates, x is the coordinate for one axis. Now for 3 coordinates, y is the wave function for one coordinate. Now you take psi is the wave function for 3 coordinates x, y, z. So y fx will be replaced by psi. Let psi is the wave function for 3 coordinates. Let psi is the wave function for 3 coordinates, or simply you can write psi. So in place of fx you put psi x, y, z. So fx is the coordinate for one coordinate, function for one coordinate, replace the wave function for 3 coordinates, psi is equal to psi x, y, z is equal to psi. So we write the here, so for 3 coordinates similar equations, d square psi by dx square plus d square psi by dy square plus d square psi by dz square is equal to minus 4 pi square psi lambda square. So this is the equation for 3 coordinates. Now put the value of the, let us take the use of de Broglie equation. De Broglie equation, that lambda is equal to h by mv. Here is lambda square. So the lambda square will be equal to h square by m square into v square. So in place of lambda square you put h square, m square, v square. So the equation will be equal to d square psi by dx square. So d square psi by dx square plus d square psi by dy square plus d square psi by dz square is equal to minus 4 pi square by m square v square by h square into m square v square. So this is h square, here it is m square v square, that is equal to, so this is the equation. Now you consider the energy of the electron. The energy is equal to total energy, kinetic energy plus the potential energy. So kinetic energy is equal to half mv square and potential energy is equal to V. So you bring V here, so we can write E minus V is equal to half mv square, or you can write 2E minus V is equal to mv square. Now multiply m above and below, so this will be m square v square by m, or you can multiply twice m E minus V is equal to m square v square. So in place of m square v square, in place of m square v square, you put 2mev. So the equation is del square psi by dx square plus del square psi by dy square plus del square psi by dz square is equal to, now this is, put the m square v square against it, 2m E minus V. So this will be minus 8 pi m and E minus V by h square. So if you bring to this side, this is pi square m. So you bring to this side d square psi by dx square plus d square psi by dy square plus d square psi by dz square is equal plus 8 pi square m by h square E minus V, and here it is psi there. even if psi is equal to 0. Here it is psi is there. So, this expression is called Schrodinger's wave equation. This is called Schrodinger's wave equation. Since it is a longer equation, lengthy equation, we can write in a simple form, that is del square psi plus 8 pi square m by h square E minus V lambda is equal to 0. Where lambda, this is the also Schrodinger's wave equation, where lambda square is called Laplacian operator. Where del square is equal to d square by dx square, d square by dy square plus d square by dz square. So, this is Schrodinger wave equation, derivation of Schrodinger's wave equation. So, what is its importance? What is its significance? Significance of Schrodinger's wave equation. So, by Schrodinger wave equation, using the Schrodinger equation for hydroatom, we can calculate the energy of hydroatom. Using Schrodinger's wave equation, we can calculate the energy of hydroatom, the energy of hydrogen atom. Not only energy of hydroatom, but hydrogen-like atoms. That is, we can also calculate the energy of helium, energy of lithium 2 plus, hydrogen-like atoms, which contains 1 electron. Second is, by solving the Schrodinger wave equation for hydrogen atom, we can find out the quantum numbers, three quantum numbers, that is n, l and m. That is principal quantum number, azimuthal quantum number and magnetic quantum number. And also they are restricted value. That means n will take not 0, n will take 1, 2, 3 like this. This is calculated from the Schrodinger's wave equation for hydrogen atom. And similarly, L will take 0 value. This will not take 0, this will take 0 value 1, 2, 3 up to n minus 1. This can maximum take n minus 1. So, this restriction value is calculated from the Schrodinger wave equation. Similarly, m takes the value minus L to 0 to plus L. So, these three principal quantum numbers, as well as the restriction value calculated by using the Schrodinger wave equation. So, these are the two advantages of Schrodinger's wave equation, but there are some demerits or limitations of Schrodinger wave equation, limitations. The first limitation is, so we cannot calculate the energy of multi-electron atom, energy of multi-electron atom. Multi-electron atom we cannot calculate by using Schrodinger wave equation. Second, similarly, it is applicable to microscopic particles, not to macroscopic particle systems. So, these are the two limitations of Schrodinger wave equation. Now, let us come to see what is the physical significance of wave function. Physical significance of wave function. That means, what is the significance of wave function which is used in Schrodinger's wave equation? The physical wave function of, so psi is the amplitude, psi represents the amplitude, psi represents amplitude, because y is replaced by psi, y represents amplitude, so psi also represents amplitude. Now, the Max Born suggested the amplitude of light as well as the amplitude of sound will give measure the intensity of light or the sound. Similarly, this principle will apply here. So, the square of the amplitude, that means psi square, will measure the electron density. So, psi square will represent the electron density. So, it measures the probability of finding the electron in a particular state. So, psi square at any point, measures the probability of electron density, that means probability of finding the electron. So, psi square is the region where the probability of finding electron maximum is called orbital. So, psi square represents the orbital where the probability of finding the electron is maximum. Now, the psi may be real or imaginary. Psi may be your real or imaginary, but the psi star or psi square is always real. Is equal to a square plus b square. So, psi square is always a real function. Now, psi means your wave function. Which wave function is acceptable, or it is called well behaved function. Which wave function is acceptable or well behaved function, that is called well behaved function. So, wave function is called a well behaved function, that means wave function is acceptable. So, which wave function psi is acceptable? It is acceptable under three conditions. Number one, it must be single value, must be continuous, must be finite over a space, over a volume. So, it must be single value, must be continuous, must be finite. It must be single value. Suppose you take the equation y is equal to mx plus c. So, y is a wave function. For a single any single value of x will get one value of y. That means it is a single value, it is acceptable. But if you take y is equal to ax plus ax square plus bx plus c, instead of y is equal to mx plus c, you take ax square bx plus c. So, that means y is not a single value, x will have two values for y. So, y is not a single value, that means this wave function is not acceptable. If you take y is equal to x square, then only x will be maybe root over plus sign or maybe minus sign, maybe minus x. That means this y is not acceptable, this y is not acceptable, but this y is acceptable. So, it must be a single value. Second is it must be continuous, that means the wave function must be continuous like this, or it must be like this, or it must be like this. It must be continuous, but the wave function should not be discontinuous. That means if it like this is for infinity, this is not acceptable. If the wave function will like this, then this will not be acceptable. So, it must be continuous. Second, it must be finite, means suppose y is equal to sin x, suppose x is equal to 30 sin 30, then the value will be equal to y will be equal to half. X is equal to sin 60, the value will be equal to root over 3 by 2, y is equal to 3 by 2. If x is equal to 90, the value is equal to 1. That means it is a finite value. But if y is equal to ex, x value to infinity, this will not be acceptable. So, must be finite over a continuous volume. So, therefore, to wave function is acceptable provided it obeys the three conditions: single value, continuous and finite. Now, let us come to the normalized and orthogonal wave functions. normalized and orthogonal wave functions. What is normalized and orthogonal wave function? What is normalized wave function? A wave function is normalized. A wave function is normalized if the psi square over a space is equal to unity. That is called normalized wave function. That means if psi is a wave function, then psi square is over a space d tau is equal to 1, then it is called a normalized. That is, or psi square d tau is equal to 1, that is called normalized. So psi means, so over the tau means zeros over a volume dx and dy and dz. So this is called a normalized wave function. This is called normalized wave function. If a wave function is not normalized, suppose psi is not normalized, how to make normalized? You multiply this wave function. So a psi into a psi when d tau integrates, so is equal to 1. That means a square psi square d tau is equal to 1, or a minus 2 is equal to psi square d tau. That means you select a such a way that a psi is a normalized wave function. So you multiply, if psi is not a wave function, you select a from this value, so that multiplying a with psi will get the normalized wave function. So where a is called normalization constant. So thank you. We will see next class other topics.